genetics might not be the most appropriate test in certain scenarios, right? It shows you your
most scenarios.
Most scenarios.
Most scenarios. Genetic testing is not appropriate.
So why? Well, let's get into that. In what scenarios would genetic testing be appropriate?
Yeah, so if you have like Huntington's or you're suspected of having Huntington's, genetic testing is fantastic because it is a gene with very high penetrance. And if you have that gene, then necessarily, unfortunately, you will die of Huntington's, which is a terrible, terrible thing to have. If you have, for instance, a condition that we recently did a study on, we haven't published it yet because we're going to patent the biomarkers. And so we want to make sure that IP is secured before we go out and publish it in the peer-reviewed literature. But it's a profiling of FOP, fibrodysplasia ossificans progressiva, which is an incredibly rare disorder that is necessarily caused by a cluster of 3 genes. And when we look at that, we say, okay, there are some phenotypic tells, and a very astute pediatrician would know that this child has FOP, but it's incredibly rare. It is an ultra rare disease. There are like 8 living people in the world who have this condition. Incredibly rare, right? And so the awareness of it isn't there for the physicians as well. They will have like a cleft in their palm and their feet, but it's a minor one sometimes, and it's often overlooked. Why is that harmful? Well, because for these people, if they have a slight injury, then the soft tissue begins to ossify, right? You have osteoclast activation and diminished osteoblast activity. So what that means is the cells that are responsible for building bone are going crazy, and the cells that are responsible for consuming bone are lazy. And that leads to this ossification of connective and soft tissues. So a lot of times they won't know that they have this condition until they're in adolescence. They're playing on the playground. Maybe they break something or they bump something. And then suddenly they'll see that around that injury site, you have this bone tissue that's growing, and their connective tissue turns hard. And if you've ever seen the skeleton of somebody with FOP, it's a prison, right? It's all fused together. Extra bone has grown. The skeletons are, I mean, there's no other word for it. They're ghastly, and it's tragic, and it's heartbreaking. And a genetic test at birth can identify these individuals very quickly and not leave them, to live their lives as ignorant of their condition, and then potentially, which leads to various other clinical sequelae. They'll have a bone break or something. The bone will grow back massive, and it'll eat some connective tissue, and they'll go in and do a surgery to remove that bone, and then the bone grows back even more. And so they often die contorted in these incredibly heartbreaking positions. And when their skeletons are in displays, there's a famous collection of them, I think in Pennsylvania, and you see the skeleton of somebody with FOP. They're contorted, they're completely fused. Their ribs, for instance, will be completely, the scapula will fuse over the ribs, their bones and their shoulders, and all the connective tissue will just be completely ossified. So for those conditions, genetic testing is a must, right? But when we talk about the things that affect most of us, heart disease, cancers, neurodegenerative disorders, these are not genetic conditions in the sense that there's not one gene or even a set of genes that can necessarily predict the onset of these things.
Propensity, or it kind of shows the map of what you might be predisposed to, but it's not showing you what's going on in your body and how you're expressing, because it's multifactorial, right? So like
gene environment,
like you said, cancer is not, you don't have the cancer gene. You might have a propensity towards cancer or what have you, but it's the environmental factors. It's your diet, it's your lifestyle, it's your metabolism, 100%. How that's functioning.
100%. And there's very good use cases where, a genetic test will necessarily stratify people for treatment response, right? We know that certain people with certain genes respond better to certain therapies and such, but that doesn't mean that people with those genes necessarily are developing, let's say you have an APOE4/4 gene, right? It's the highest risk factor often seen in people with familial Alzheimer's. However, there are people in that group that don't develop Alzheimer's, an appreciable number, such that the predictive accuracy of that gene is quite low. When we look at the predictive accuracy,
documentary. I think Chris Hemsworth or one of those famous actors did a documentary, and they're like, hey, you're 10 times more likely to get Alzheimer's. And then they created this big emotional thing. I didn't see the full thing, by the way, so I might be somewhat inaccurate in this, but kind of a big emotional thing. And now he's going on this journey of like essentially beating Alzheimer's when he just had the predisposition, or he was more likely to develop Alzheimer's, but didn't actually have necessarily indicating anything. Nothing was indicating that he actually had it or was going to acquire it. And so it was kind of looking at totally from the wrong angle of this thing of how to perceive this. So
listen, if we were, 100%, if genetics were the answer, then the completion of the Human Genome Project would have solved everything. Has it? No. That's because genetics is not the end all be all. And again, for most of the conditions that are hunting us down and killing us, like Alzheimer's, these are complex gene environment conditions. Their etiologies are far more heterogeneous than something like Huntington's or FOP. And the genes that are implicated in them, for instance, for cardiovascular disease, there's a couple thousand genes that each account for a small proportion of variants. Right. And even if we were to model them all, the accuracy of developing CVD can be largely mitigated and reduced if somebody just has a healthful lifestyle. They are again nudging you toward a conclusion, but that conclusion can be rewritten by your behaviors. For most of the things that kill us, that is the case. And so so that's kind of my approach to this. And that's what we see in the omic sciences, right? Genomics is important. When I'm asked to provide my opinion on LinkedIn for various things, and I get to see the polls of other experts in this, multiomic in vitro diagnostic group I'm in, nobody thinks that genes are the answer. Really, we think that, it's the last thing we really want to consider. Why
is it tested so widely then? I mean, you see so many companies out there that are get your genetics tested so that we can understand what to supplement you with. And does that have any bearing? Or if it doesn't, then why are so many companies utilizing this as the basis for how to approach health?
Yeah, Mike, a great question. One is that, there's many reasons. When you go test with 23andMe, for instance, they engage in scientific research. They will, that data does then get sent over to people who can use it for scientific research.
And the government.
And the government or dark web leaks or whatever else. Yeah. So that is absolutely something that I think is a great angle. Not just to, sell test kits. That's a tertiary consideration at best. It really is to, provide, this meaningful data, this subset of data that can be used in research. The other thing I think is, however, just to sell test kits. People are aware of the genome. People, right? We have to educate people on the metabolome. We have to educate people on the proteome or the transcriptome. People are aware of the genome, and there's a growing appreciation, obviously, for the microbiome. But they've been hammered that, your genes basically control everything. Your genes, basically, you can't do anything outside them, right? That's true. You cannot defy them in the sense that if you have, a gene, let's say your, MTHFR gene is you have a variant that will necessarily reduce the activity of the expressed enzyme, the expressed protein. That's true. You cannot change that expression. Right. What you can do, however, is take that MTHFR, right, and then feed it better substrates so that the enzymes that are there still work efficiently, right? The activity of the enzyme, even if it's impaired, the affinity is impaired, the numbers of that enzyme are lowered. You can still feed it more food, right? And it'll still roughly perform the same. There are ways to mitigate genetic expression. And it sort of is
that valuable? Because for example,
only in the context of another.
I want to work with 10x Health, right? We're having some conversations with. Well, I shouldn't say that because I don't think we're supposed to say that kind of thing until there's something solid. But we've talked about potentially, hey, what would it look like for our testing platform to be involved with what you're doing? But they're testing everybody on a genetic basis and then providing supplementation. So how much actionable result does that produce for people in terms of feeling better, performing better, et cetera?
Yeah, well, to the best of my knowledge, 10x Health is doing a methylation test of 4 genes. It's not even like a whole genome sequence, right? So you're not getting your whole genome. You're getting a genetic test.
Yeah.
Yeah. It's 4 genes, and they reflect 4 different like methylation parameters.
And just to be clear, this is not knocking on them by any means. Like we hope to.
No, it's the truth. It's the truth.
Provide them something that could even be more valuable. And it's not to say that there's no value there. It's just like there's accelerations in how we understand science and things. And obviously we're a little bit cutting edge and small. So people are still like growing in awareness of all the things that you're offering and how cutting edge that is. But I think there's always room for improvement. And so hopefully we see that to be the case. But anyway, I just wanted to make that disclaimer.
So that's great, Micah. Yeah. I mean, we, I will say this, that, those genetic tests and the supplements that they give, there's a lot of colloquial, I guess, evidence, like it's anecdotal. There's no scientific evidence really that this works. There's no clinical trial. There's no, as far as I know, even attempt to show scientifically or empirically that this works, but they have some happy customers. They also have, I think, some non-happy customers because methylation only explains 1 to 5% of your total metabolic reactions. Methylation is not the end all be all. I can name a couple dozen other types of reactions that happen in the body that are not methylation. What is methylation? That is adding a methyl group to something. You also have decarboxylation, carboxylation, glycosylation. You have dehydration synthesis. You have hydrolysis. You have very many different things that are taking place. And methylation, or adding one methyl group to a compound, that conjugation, a very small portion of phase 2 metabolism, which is, again, just modifying compounds. That is, again, 1 to 5%, depending on the rate of methylation. You are not taking into account all of the other oxidation, phosphorylation. What about those processes? Are you saying they're not important? Of course they are. And I think when you focus too much on, methylation and 4-methylation genes, they have fantastic presentation. They almost convinced me. But I would say that, ultimately, it's going to come to a grinding halt because people are going to realize that it's not working as it should have, because it's not addressing the biochemistry holistically. When you have something like whole genome sequencing, that's very powerful. That's not 4 tests. It's not 4 genetic markers. It's the whole genome. And when you combine that with something like the metabolome, now we're cooking with gas, right? And that is something that Theriome is striving toward, is to include more tests of the systems biology in order of relevance to general health. And the genome is last on our list because when we look at the variance that every level of systems biology explains in outcomes of individuals, the genome is the least predictive. It is the least amenable to change. It is non-dynamic in its change, right? Like transcriptomic changes are sure to happen, and they're dynamic. The epigenome may change, but the genome does not. And so when we talk about its expression through time, we have a paper coming out in Genome Medicine discussing, it's a review paper and an opinion paper kind of merged together. We're discussing, the temporal changes in response to stimuli across these omics levels. The genome is flat, right? And the predictive value is very low, right? For something like cancer, it'll be like, I tested you for BRCA1, 2, you have a 20 to 80% chance of cancer. Okay, what am I going to do with that? What am I going to do as if I'm a woman who has a familial history of breast cancer? How do I know if it's 20% or if it's 80%? Because guess what? Those are appreciably different, right? And so the predictive value is low, and there's no change in its expression. There's no value in retesting and realigning based on that data because it doesn't change. And so we are going in order of importance to human health. And that first is the metabolome. After that, it is the microbiome. And then we'll go to the proteome, transcriptome, and then eventually genome. We're sort of reverse engineering the central dogma of biology. And that's because it's an order of how relevant they are and how predictive they are to future health events, and necessarily how much they change in response to interventions that we may recommend. I think the integration of omics This is where everything is going. The future is 100% multiomic. You will, in 20 years, hopefully, go to your regular physician office and they won't run a CBC. They won't run a liver function test. They won't run these sort of discrete things that each look at anywhere from, 2 to a couple dozen parameters. You will go into a hospital or clinic setting. You will have your entire genome, on record. You will have your most recent RNA profiling, your most recent proteins, and it'll be hundreds of proteins, not just cholesterol, HbA1c, all of your hormones, all of the immune-related proteins. Everything can be done in, a high throughput multiplex assay that can look at 900 proteins at once. You'll have, 600, all of your, bugs and archaea and fungi and viruses and parasites and everything known about you in your gut. And then you'll also have, your blood metabolism, and you'll have not just a couple dozen, but 100 plus, or even hundreds or thousands, right? We have the capability at Theriome to profile 9,000 metabolites in the blood. What we've done in the consideration of analysis, cogency, and cost effectiveness is reduce this to 126 sentinel metabolites. But if somebody wanted to get 9,000 metabolites performed, we have the technology to do that. The implementation currently is not as feasible because it costs so much. It would be a $5,000 assay. And so that's
inexpensive.
Right. And that's almost at cost. Yeah, that's almost at cost, right? So we really, and we've published this. So I have a publication in analytical chemistry in my early days of my doctoral program known as database assisted globally optimized targeted mass spectrometry. It rolls off the tongue, but it is essentially a database that is linked onto the analysis and can classify metabolites based in real-time corroboration with this database and their chemical compounds and base peaks they give off and everything like that. So we can do 9,000. That's not an issue. It's the issue that who's going to pay for that? Who is going to make sense of that? It is an information overload. We need to sort of develop more sophisticated algorithms, which we are also working on. But in the future, you'll have all of this ideally on blockchain. And when you go to a new clinic, a new hospital system, you go out of this country into another country to seek help or receive medical attention, you will have your wallet ID, right? You will have your sort of area where all of your electronic health records, including your genome, your latest transcriptome, all of your, historic levels of your metabolome, all put into that, blockchain, and you can carry your health record around with you as easily as you carry around your Bitcoin and disseminate that with your consent to only the people that you consent to for a specific number of time. And after that, it's revoked. That is the future of multiomics. And coupled with, this advance in AI and blockchain, it will get to a point where we're making more sense of this data and we package it in a way that can be disseminated in a trustless, transparent, auditable manner with the utmost informed consent provided by the person who gave the sample.
Yeah, and not to mention too, I have a couple of points, but first of all, that with Theriome, part of what we're doing is we're building this great base of data and information that is owned by you, whoever has that data. And he said, as easy as your Bitcoin. If you don't know how easy it is, I could show you in 2 seconds, like my Bitcoin wallet, right? But it provides a point of contrast because there's so much in the blood, in the body, in the system that we don't know about yet. So this data provides a point of contrast that we can now study and get an understanding of what is happening in the body with metabolites that perhaps haven't been studied or factors in the genetics that haven't been studied. And so we'll be able to publish and get a much better understanding of what's going on in the body very, very quickly as we're getting that body of data. But the second thing I wanted to say was about, my initial question was, why do you think genetic testing is such a factor in how people are perceiving their health? And I think it's actually part of the reason is because, well, I should say this. I think you are in a very unique position to speak about this because you are highly educated, obviously intelligent in the area of multiomics, which is understanding the system's biology. So essentially, you have a very high level view of hey, at a basic level, this is how the body works. You look at this, then this, then this, then this. And these are the things that are weighted in priority of what is going to have the biggest impact on somebody's health. Whereas when you go and just like look at the literature looking for the thing, if you were to look at methylation and say no methylation, that means you die. It's like, yeah, obviously, but there's so many things that you can extract and say, like, if this is deficient, if this is low, if this is that, it's going to have this negative effect. However, that's not, if you're just looking at like that study, right? Like methylation, right? But then you come along and say, well, that's 1 to 5% of what is happening in your body. So if you're looking at that, you're really looking in a silo of that 1 to 5% and not necessarily saying like, hey, how do we get an understanding on, 95% of the body and what's happening with 95% of it? Not only where you can go, but where you currently are and what you can do about it. And that's the position that I think you're bringing to this industry in a very needed way. That's speaking at a high level, saying like, these are the things that are really important to look at. It's not just genetics. It's not just methylation. It's not just X. And we take a holistic viewpoint, which people in this space are, they have a propensity for that, right? They understand the idea of holistic viewpoint, not just symptomatic coverage, not just looking into a silo, but understanding the bigger picture and what we can do about it. And that's I think it comes down to, this is not entirely new science, but it's relatively young and we're growing in our understanding of it. So there's some growing pains with that, right? The industry is kind of catching up, and you're very much at the forefront of it, pushing that line into the future. Yeah. Whereas people might be, a couple years behind, a few years behind in understanding how this works. And then beyond that, also not understanding the full scope of what you can potentially do with all this information.
And this is, I think a symptom of just human psychology. We love heuristics. We love heuristic patterns where we can say, give me the shorthand. What's the shorthand, right? Like, and the answer is, when it comes to the functioning of the most complex organism that we know of, us, there are no simple answers. And when you start to look for simple answers, you lose the forest for the trees. And obviously, when that happens, at best case scenario, the things that these companies are telling individuals to supplement with and do are ineffective, or worst case scenario, they could be harmful. And so when you rely on that simplicity, don't be surprised if what you're doing isn't moving the needle and your customers sort of grow disinterested.
It could be moving it incrementally too, in a small way, right? Like
sure.
If I go from walking 1 mile to 1.5 miles, it's still an incremental improvement.
It's an incremental improvement. And you should never underestimate.
It's not going to have a massive effect on like weight loss or something, right?
Sure. Yeah. So it'll have an effect on your arteries. It probably won't affect your weight, and you should never underestimate, the cumulative effect of consistent, even although small, improvements. That is true. Although when you address the system as a whole, the improvements are rapid and they're vertical. Right. So we address, let's say somebody comes in with heavy metal toxicity. We find that we give them an incredibly specific and detailed detoxification protocol, everything ranging from prescription chelation therapies to infrared sauna and hydration and everything in between. They are supposed to, retest in 3 months. Any one of these would have worked and it would have been an incremental improvement, or all of them can be packaged into one, given the results of an individual's health test. And then we get those, delightful emails 2 weeks into it that say, hey, I'm significantly better already. Should I continue? And it's like, yes, continue. But that is a vertical and quick advance. And that only happens when you address the system as a whole. And these, this whole idea of like, I'm going to try something for a couple of weeks, see if it works, and I'll try something else a couple of weeks, see if it works. This is, again, because we didn't have the technology to perform something like digital twinning, where I can take 1,300 interventions, everything from, let's say, prescription medication, metformin for glucose homeostasis, metformin for breast cancer recurrence, or I can take it and say, okay, I'm going to do, metformin here, and then you got supplementation, diet, exercise, all these things that you can do. What if we were to simulate that on you 1,000 times with 15% randomness built in to tailor that intervention to your specific needs. We can do that. You don't have to go try 1,300 different things each 1,000 times with slight variation to find what's best for you. We can do that in silico and spare you the time and cost of experimentation, right? And tell you this is what's predicted to be the best. And then at retest, we get an even more sensitive idea of how they responded. And the second round of digital twinning recommendations are even more granular and custom fit to their needs. And so, because now we have a measure of their response and not just a postulation and extrapolation of how they would respond. So it is this effort in systems biology that we need to collect more data and we need to analyze that better. I would say that the most pressing concern in systems biology right now is that we have a data management crisis. We really do not have all of the tools built out yet to accommodate, 5-layer multiomic analysis quite yet. We have like a gene ontology analysis. We have joint pathway analysis where we can upload, genome and metabolome information on the Homo sapien and then see some, very interesting relationships and what's expressed, what's not. How do single nucleotide polymorphisms affect downstream metabolism, and answer some of those questions. What we are doing currently are, so much integration between the microbiome and the metabolome. We know the microbiome is the second most important level of your omics. And that microbiome interacts with 50% of the known metabolome. We have these tools like MMVec, like other neural network analyses that we implement to find co-occurrence or to find consumption and production patterns between the gut microbiome and the systemic metabolome. Our recent paper hopefully is coming out in Nature Communications very shortly. We replied to the reviewers, and barring a second round of revisions, I think we should be good to get that accepted. That is a paper where we're looking at the joint microbiome and metabolome and utilizing these very advanced AI analyses to look at the effects of intermittent fasting. So this is a follow-up paper to our paper that was published in Frontiers of Nutrition. This is a much more in-depth and sophisticated paper. So it's thankfully being published hopefully in Nature Communications. And what we have here is this idea that these are the two most important layers of omics. And by analyzing these, we can more accurately speak to health outcomes than if we were to focus on the genome right now. In the future, once we have everything built out, I think it's honestly game over for disease. If we can have a database of 10,000 people, even a modest database of 10,000 people on which, let's say 50% we have longitudinal samples from, and on 100% of which we have all 5 layers of omics, we are looking at one of the most important breakthroughs in health science, is to have this incredibly well curated. The biggest database I know of outside of that is a database that looks at the transcriptome, microbiome, and metabolome, ignoring the genome and the proteome. And that database is like 7,700 people. That is the closest we've ever gotten. And it was not a commercial database. It was a research project that ended up creating this very big database.
I don't know that it'll be game over for disease and the in a lot of senses, because people with lung cancer continue to smoke knowing they have lung cancer.
Right. It doesn't take into fact the human error, right? The human behaviors and the human things like
what
that.
we want to do. I mean, right. And that's so much of disease, even currently. Like I know an individual who is not doing well, becoming less mobile, gaining weight relatively rapidly. And they, set some intention to eat well and then just never follow it. It's just all interest and having fun and that
absolutely
kind of thing. And
I mean, in the sense of what is causing amyloid beta deposition? What is causing
scientific?
Yeah. We want to know molecularly what's happening. We don't really know. I think a lot of people, for instance, let's talk about like Ozempic. We know what it does in 2 or 3 different, pathways, but it has so many off-target effects. What about metformin? Metformin, we have an idea that it affects, AMPK, it affects mTOR, it affects various other important pathways, but we have no idea everything else it does. And every time there's a study on metformin, it comes up that, here's another unintended off-target effect we've discovered. And it just keeps growing, right? And so we don't understand even the therapies that we're giving for the conditions that we don't understand. I think the average person does not appreciate how much we are operating in the blind, right? Do we die at 40 years old? No, we've fixed that largely. But it doesn't mean that our health span has been increased. Our lifespan may be increased, but our health span has not increased. We don't understand disease. And to understand a disease, and this is something that the virologists do a fantastic job of, but to take something down, you must understand it down to the last biophysical interaction. And so that's what we do here at Theriome, is that we take personalization seriously down to the last molecule, and having that human atlas mapped out, that molecular atlas mapped out, it would be an incredibly important step forward. I think far more important than just the completion of the Human Genome Project.
Yeah. And we would understand Ozempic very quickly, right? Because we have this mapped out. So we take that, enter that into the system of somebody's body and have mapping of all the effects that we might not see. I started laughing on that because there was an individual, you saw that one story I posted on Instagram where it was like, I think Ozempic could, in the future years share, potentially have some issues for people, right? Because we're slowing down the gut and, we're building microbes and different things. And I actually got a lot of flack from that. And I'm not saying that there's no place for that kind of stuff, right? I'm just saying that there's these things that we do can have unintended ramifications, right?
The GLP-1 agonist. GLP-1 is everywhere. You have no idea what these things are doing. I mean, it's really kind of like, well, in our safety trials and phase 1 trials, it didn't hurt anyone that we know of. I was told
it was more natural than weightlifting. Was one of the responses. And I was kind of like, well, yeah, sure. Weightlifting isn't like picking up the rock to get the bugs underneath it to eat them, but it's pretty dang close. It's like not too different from what we would have to do in our environment to survive.
Wow. that is, it was kind of shocking. All due respect to whoever said that. That is one of the most delusional things I've ever heard.
Well, I think it was they were more upset than anything, and not. I actually really like her as a person, so it wasn't not knocking her, but
more natural.
I think these are. I think that goes to the point, though, is that these are kind of sensitive subjects, whether that's prescription drugs.
Listen, chronic use of any medication is not good. Unless you have something that, really like cystic fibrosis, you can mitigate the effects via, diet, exercise, and everything else, but you still need medication. That is not something that's going away. But like diabetes, even, this insulin, unless you have type 1 diabetes, but, type 2 diabetes can be cured. And yet we're going to spend, billions of dollars this year on just identifying new drug targets. Right. And so why are we doing that? We have the cure to type 2 diabetes called diet and exercise. Right. But the human factor, as you mentioned, prevents that from taking place. And so there's a market for it. People want to take a pill and not have diabetes. People want to take a shot and not be overweight. That's fine. But to say that it's as natural
that are going to be opportunistic over that too, right? Like
absolutely. Drug companies are opportunistic. The FDA will review anything. The FDA will review anything so long as you pay their fees. They may not approve it, but they'll review it as long as you pay their fees. And so to go through that process, they welcome that. That's their bread and butter. There is, I don't think there's this like evil, like cabal of
no, it's opportunity, right?
It's opportunity. It's natural opportunity. There's no like evil cabal of, pharma execs and FDA top brass hand in hand saying, let's kill people. That's not the case at all, but it's an opportunity where people demand these drugs to be these silver bullets to exist on the market. And there are chemists and business people in the world that say, okay, we can do that. And the FDA, which has a very flawed review process, will say, okay, give us $5 or $10 million and we'll review it for you and give you a certain amount of time to go sell it on the markets. It is a de facto cartel. It is not one that is maliciously designed and intentionally implemented. The cabal of the world leaders that
There's
are
malicious people in every industry, and
Sure.
But it's not on the scale, in my opinion, that people that kind of more of a conspiratorial take would have, right?
Yes, it's not
opportunity. It's opportunity and incentive structures provided at every level. And so somebody that is, perhaps unethical might say, how can I set up incentive structures so that this disperses through every level? And my thing is the thing that goes and makes money. And, there is some malicious intent there, right? Or at the very least, unethical. But I think it's more of a design of the system, so to speak, rather than, kind of this high level where we're getting into it. But the other thing that I wanted to say is so let's take that genetic test, for example, and the methylation. There are going to be some people that benefit from that because that was a needed thing in their diet. Let's just say, for example,
a lot of people would actually. It's more prevalent than you think. This poor methylation gene,
but I think that's part of why a lot of products can exist. And when you're a hammer, everything is a nail, right? When you have a red light company, everybody needs red light. When you have an ozone company, everybody needs ozone. When you have this or that, and I've talked about that very openly, right? I think it's just like a lot of these people view things as a hammer. They're looking in a silo, and they're trying to address things in a silo. If we were to take, let's say, aspirin, just as a theoretical example, and say this is a cancer cure or a cancer treatment, do you know how many people we could get to say this cured my cancer? Well, approximately 8%, because 8% of people have spontaneous remission of cancer. And thereby we could say that, hey, this cures cancer, and we're just looking at the 8% and then extrapolating that to the rest of the people. So that is why it's so important to have good data,
studies,
information on what is happening with a particular intervention. And then you are taking that to the next level by saying, hey, we are roping together all this data, all these studies, and tailoring that to the individual so we can 100%. Get rid of this trial and error.
100%. When you say 8%, experience remission, that is a descriptive statistic. So in the umbrella of frequentist statistics, which are things like your ANOVA, your PCAs, all the statistics that we do in an analysis for a study, we have two different types of statistics. You have a descriptive and you have inferential. So the descriptive is something that's like 8%. We experience remission, or you'll say something like, what's the average? What's a mean? What's a median, right? Or mode, what's the mode of the data? These are all descriptives. These are not inferential whatsoever. We need to then do a test and see those who received the aspirin for their cancer and those who didn't receive the aspirin, was there a significant difference? And by that, I mean, what is the chance of type 1 error? What is the chance that the decrease in the aspirin group, what was that chance that it was due to just sampling error, right? And then we look at standard deviations, we look at their overlap, and that gives us a sense of, what out of, let's say 100 chances that this were to take place, we want to make sure that the reduction that we saw in the aspirin group, that the likelihood that it was due to chance was less than 5%, right? And so we have to do inferential statistics in order to infer to the effects of the treatment. And descriptive statistics are not the case. And so I would say also to those who are watching this, be very, very cautious when people only use descriptive statistics, because there is a lie most likely there. And they are sort of lying with statistics. It's a very easy thing to do. In the famous words of Benjamin Disraeli, there are lies, damned lies, and statistics. So be careful as you read this and be hopefully an informed consumer, because statistics isn't just a little bit of math. It's very complex math, and it's getting more complex every day, especially as we foray into Bayesian statistics and artificial intelligence and machine learning methods. So absolutely, you need studies. Anecdotal evidence is not enough. We have anecdotal evidence for the aerosol test. We include it as case studies, but we also have peer-reviewed, published literature in the most high impact, most rigorous journals in the world. Nature Communications, which is one of our upcoming publications, has a lower acceptance rate than Harvard University accepts undergrads. So, I mean, it is an incredibly competitive field, especially when we talk about basic science and high science, and those are what we engage in Theriome. And once we rope in, like you said, all the layers of omics, we will have unprecedented insight into an individual's biology and be able to personalize, truly personalize what we recommend to them based on everything that we see, which will be incredible. I mean, we're really ushering in an era of medicine 3.0, where we're no longer reactive, we're proactive. We identify risks before they happen. We tailor a person's lifestyle and their life experiences to what is best for them, and we can tell them what those are. And so I'm very optimistic, and I think in the next 50 years we will undergo a fantastic paradigm shift. And with every paradigm shift comes, you mentioned catching up, but they're more like convulsions. The science and the medicine will convulse before it dies and is reborn as this systems biology multiomics approach.
Yeah, and I just want to thank you because I'm really honored to be a part of this mission with Theriome, ushering in what I really believe is like the next wave of medicine, what is truly going to be helpful and impactful to people in their lives. I think we'll see a very rapid change in how people are approaching things, and the diagnosis being less scary because we know what to do about it, or finding something early on so that grandparents can be around for their grandkids, or brothers around for brothers, and all those types of things. And it's going to have massive impact in the space. So I'm super honored just to be a part of this group and to be, in the same room with you, having these discussions and to be able to do this. So if you've been listening to this and you want to understand more about what Dr. Jasbi, Dr. Moore have created, I highly recommend going to www.therio.me/guide. You should see it on the screen right here, right now. But that's going to get you access to a sample report. So Dr. Jasbi has this comprehensive test that's looking at a lot of these things that we've talked about. And this is a building thing, right? So this company is right now doing the metabolome, which we find to be the most impactful for people's health state right now. But where in the future, we're going to be layering in the proteomics, so the proteins, the transcriptomics, microbiome, genome, all those different layers so that there's even more depth of understanding. So you'll get the sample report on the metabolome, which can be quite insightful into one's health with the 12 key health domains, metabolic health associations, and then the personalized protocols, which includes those thousands of simulations to see what's going to work best for you. So there's that sample report. And then there's Dr. Jasbi's book that's totally free that you can get just by going to that link. So that's going to outline a lot of what he talked about today, but in much more depth and with more context and more subjects that he touches on in that book. And the third thing that you'll find once you go to that link and you get the sample report, you get the free book, is that you can actually schedule a time with Dr. Jasbi one-on-one to better understand this test. So I especially encourage clinics to do that. You might be considering, how do I onboard this for my patients? Dr. Jasbi can get into the nuts and bolts of how this exactly works, even go in more depth on the science and help out in that respect. So thank you, everybody, for listening. It's been a pleasure, Dr. Jasbi. Thank you so much.